After learning this module, you shall be able to understand what is a Tobit model and when is it useful. Also, we would discuss and learn about the estimation of Tobit models and the marginal effects in Tobit models. Let me introduce these Tobit models to you. In many of the time, we get censored and truncated series in social sciences. In the 1980s, there was a US federal law restricting speedometer readings to no more than 85 miles per hour. Let me make it clear, in US they measure speed in miles and not in kilometers. So if you wanted to try and predict a vehicle's top speed from a combination of horsepower, engine size, you would get a reading no higher than 85, regardless of how fast our vehicle was really traveling. This is a classic case of right censoring, censoring from above of the data. The only thing we are certain of is that those vehicles were traveling at least 85 miles per hour. Now consider a research project is studying the level of lead in home drinking water as a function of the age of a house and family income. The water testing kit cannot detect lead concentrations below 5 parts per billion, which can be denoted as ppb. Lead levels above 15 ppb are said to be dangerous. These data are an example of left censoring or censoring from below. For example, if we are dealing with household durable expenditure, we know that for certain values of income, there won't be any expenditure on durable goods. Once the household has a certain level of income, then only they will incur some expenditure on durable goods. The specification below therefore gives it formally, and L is 0 for the below example. Such censoring is called censoring from below or censoring from left. So let us denote y equal to z as a function of y star. Y is equal to y star if y star is greater than L and is equal to L if y star is less than or equal to L. There could be one example where we have data on income and we assign a value of 1 lakh to all the income level beyond 1 lakh. Such situation will lead to censoring from the above or censoring from the right. Now, one important thing about censoring is that the value of independent variable is observed for entire population, but the value of the dependent variable is visible only for a range of dependent variables. For example, y we may say is equal to z is function of y star and y is equal to y star if y star is less than u and is equal to u if y star is greater than or equal to u. We could have another possibility known as truncation, in which we don't observe both independent and dependent variables for a range of our population. If we don't observe sample elements below a certain given value, this is known as truncation from left or truncation from below. We express this as y is equal to z y star and y is equal to y star if y star is greater than L. If we don't observe sample elements beyond a certain given value, this is known as truncation from right or from above, and we can write now y is equal to z as a function of y star, and we can say y is equal to y star if y star is less than u. Let's have a graph. Now this is a graph of Tobit, which is censored and truncated means. In this graph, we have different conditional means on the y-axis and we have natural logarithm of Bayes on the x-axis. We have scattered values, and I'm sure you can see the truncated mean, the censored mean and uncensored mean on these lines. And we have the actual latent variable on as the scattered points. So consider the following labor supply data from Cameron and Trivedi textbook, which is 2005 publication. In this, we know y star is equal to minus 2500 plus ln w plus e, and e is distributed normally with mean 0 and variance 1000 square. Ln w is distributed normally with mean 0.75 and variance 0.6 square. The above model, based on generated data, gives an overview of the idea of censoring and truncations. The model implies that the Bayes elasticity is 1000 divided by y star, which equals, for example, 0.5 for full-time work, which is denoted as 2000 hours. So for each 1% increase in Bayes, annual hours increase by 10 hours. Graph 1 presents a scatter plot of y star and ln w for a generated sample of 200 observations. The conditional mean for y would be same as unconditional mean of y star in case of non-censoring, which is given by y star is equal to minus 2500 plus ln w by the lowest curve, which is a straight line. Now this includes the observation of y star less than 0 as well. If we do censoring, then the y is set to 0 for negative values of y star, as people with negative desired for work hours will not work at all. And in that case, we can write y is equal to z as a function of y star, and y will be equal to y star if y star is greater than 0, and y will be equal to 0 if y star is less than or equal to 0. Approximately 35% of the sample suffers from this. And the moment we replace these negative y stars with 0, the conditional mean of y is obtained, which is certainly higher than the previous case, as many negative values are replaced with 0. So it has little impact for high wages, since then few observations on the y star are 0. Now the same can be seen from our graph 1. With truncation at 0, the 35% of the population with the negative values of y star are dropped altogether. Y is, again, we can say is a function of z, which is a function of y star, and y is equal to y star if y star is greater than 0. Now this increases the mean above the censored mean, since 0 values are no longer included in the data used to form the mean. It has little impact for high wages, since then few observations on y star are 0. Now the same can be seen from graph 1 again. Consider the labor supply data from Cameron and Trivedi 2005. Y star is equal to minus 2500 plus ln w plus e, and e, as we said earlier, is distributed normally with 0 mean and 1000 square as the variance. Similarly, we know ln w is distributed with normally with the mean 0.75 and variance 0.6 square. If we do a censoring from the above censoring, then the y is set to be 0 for all positive values of y star, and y is now equal to zy star, and y is equal to y star if y star is less than 0, and this will be equal to 0 if y star is greater than or equal to 0. We know approximately 65% of the sample suffers from this, and the moment we replace these positive y stars with 0, the conditional mean of y is obtained, which is certainly lower. So with truncation at 0 from above, the 65% of the population with positive values of y star are dropped altogether. And in that case, y is equal to zy star, and y will be equal to y star, and that is if y star is less than 0. So this decreases the mean below the censored mean. Now figure 2 will show that, and since 0 values are no longer included in the data used to form the mean, and we will look at graph 2. So in this graph 2, we again have the censored and truncated means for different conditional means. It is clear that censored and truncated conditional means are non-linear in X, even if the underlying population mean is linear. OLS estimation using truncated or censored data will lead to inconsistent estimation of the slope parameter. Since by visual inspection of figures 1 and 2, a linear approximation to the non-linear truncated and censored means will have a steeper slope than that for the original untruncated mean. Analysis should instead be based on the formulas for the censored or truncated conditional mean. Let us try to understand the concept of expected value in such situations. Now, expected value of y is given by the expression below in case of truncation from below, and you can see the appendix for more details. The expected value of y is now equal to x beta plus sigma delta into x beta upon sigma, where delta is the inverse Mills ratio. Inverse Mills ratio, named after John P. Mills, gives the ratio of probability density and cumulative density, and can be defined as lambda is equal to f, a function of x beta upon sigma, divided by capital F x beta upon sigma. As again, let me repeat, a small f is the density function and capital F is the cumulative density function. We can see that the expected value from the truncated value would be greater than the expected value without truncation, as many negative values are not taken into consideration while calculating expected values in the truncated case. In case of sensing from below, the expected value therefore is given by expected value of y is equal to double brackets x beta plus sigma lambda into x beta upon sigma, brackets closed, is into capital F into x beta upon sigma. Now this on simplification is equal to x beta into capital F into x beta upon sigma plus sigma into small f x beta upon sigma. Now this would be less than or equal to the truncated mean, as capital F into x beta upon sigma is less than or equal to 1. Now, as is clear from the Mills ratio in our graph 3, the difference in the truncated and censored mean and normal mean would be more and more for negative values below the limit. You can see it from graph 3, which gives us inverse Mills ratio, a 8 D's S cutoff varies. Now we have inverse Mills ratio, we have the cumulative density function and the density functions here in this graph, and we have x on the x-axis. Now expected value of y is given by an expression shown below in the case of truncation from above. Again, you can look at the appendix for the details. But now we can express expected value of y equal to x beta minus sigma lambda into x beta upon sigma, where lambda is again the inverse Mills ratio. and now lambda is defined as small f x beta upon sigma divided by 1 minus capital F x beta upon sigma. So we can see that the expected value from the truncated would be less than the expected value without truncation, as many positive values are now not taken into consideration while calculating expected values in the truncated case. In case of sensing from above, we can write down this expected value of y to be equal to x beta minus sigma lambda into x beta upon sigma whole multiplied by f multiplied by minus x beta upon sigma. This is multiplied by x beta star 1 minus f x beta upon sigma minus sigma into small f x beta upon sigma. Now this would be greater than or equal to the truncated mean, as we know that capital F into minus x beta upon sigma is less than or equal to 1. We can again look at it from graph 4, where we have the inverse mean ratios as cutoff varies. Now it is clear from the Mills ratio in this graph 4, the difference in truncated and censored mean and normal mean would be more and more for positive values above the limit. Now one important observation from above is that the expected value in case of censoring is equal to the expected value of truncated multiplied by the probability of the truncated distribution. Having understood these nuances, let us now look at the marginal effects in this section. Now marginal effects in case of left truncated can be expressed as the partial derivative of expected value of y given x with respect to x is equal to derivative x beta plus sigma lambda of x beta upon sigma whole divided by partial derivative of x. Now this comes out to be equal to beta into 1 minus x beta upon sigma into lambda minus lambda square. Now marginal effects in case of right truncation is expressed as derivative of partial derivative of expected value of y given x with respect to x is equal to partial derivative of x beta plus sigma lambda into x beta upon sigma whole divided by partial derivative of x, and this is equal to beta plus x beta upon sigma into lambda into beta plus lambda square into beta. Now marginal effects in case of left censoring could similarly be expressed as partial derivative of expected value of y given x with respect to x equal to lambda or partial derivative x beta plus sigma lambda x beta upon sigma whole multiplied by a function capital F into x beta upon sigma whole divided by partial derivative of x. So in a way we are taking partial derivative both in the numerator and denominators. Now on simplification, this comes out to be equal to capital F multiplied by x beta upon sigma into derivative of x beta plus sigma lambda into x beta upon sigma divided by partial derivative of x. This is now added to x beta plus sigma lambda x beta upon sigma into partial derivative of f into x beta upon sigma whole divided by partial derivative of x. Now marginal effects in case of right censoring similarly could also be expressed in the form of a formula which is given here as partial derivative of e or expected value of y is partial derivative of x beta minus sigma lambda into x beta upon sigma whole star into f star minus x beta upon sigma divided by partial derivative of x. Now this on simplification has again two expressions. The first one is that this is equal to f into minus x beta upon sigma into partial derivative of x beta minus sigma lambda of x beta upon sigma divided by partial derivative of x plus x beta minus sigma lambda function of x beta upon sigma multiplied by partial derivative of f into minus x beta upon sigma whole divided by partial derivative of x. Now, thus we know that the total change in y can be disaggregated into two very intuitive parts. First, the change in y of those above the limit or below the limit, that is the truncated part, weighted by the probability of being above or below the limit. And the second part is the change in the probability of being above or below the limit, weighted by the expected value of y if above or below the limit. If we divide marginal effects in case of left censoring by beta star into, in bracket capital F, into x beta upon sigma, that is the total marginal effects in the case of left censoring, then we can see that the partial derivative of x beta plus sigma lambda of x beta by sigma whole divided by beta into partial derivative of x is equal to 1 minus x beta upon sigma into lambda minus lambda square. Now this is the fraction of change due to change of those above the limit. If we divide marginal effects in case of right censoring by beta star into f multiplied by minus x beta upon sigma, that is the total marginal effect in case of right censoring, then we can see that partial derivative of x beta minus sigma lambda of x beta divided by sigma whole divided by beta into partial derivative of x. And again this of simplification is equal to 1 plus x beta upon sigma into lambda plus lambda square. And this is the fraction of change due to change of those below the limit. Now let us try to understand the estimation of such Tobit models. A Tobit model is basically a censored model from the below or from above or both. So now consider a Tobit model censored from below. So let's presume that y star is equal to x beta plus epsilon, where epsilon is again distributed normally with mean 0 and variance sigma square. We can again say that y will be equal to y star if y star is greater than 0 and will be equal to 0 if y star is less than or equal to 0. Therefore, the density function fy given x is now equal to fy star given x if y star is greater than 0 and is 0 if y star is less than or equal to 0. Now this density function fy given x is distributed normally with x beta and variance sigma square if x beta plus epsilon is greater than 0, and this density function will be equal to 0 if x beta plus epsilon is less than or equal to 0. We can say that density function f of y given x is equal to 0 if epsilon is less than or equal to minus x beta, which means we have taken x beta to the other side with a negative sign. So on simplification, this density function, which is f of y given x, is now equal to f star 0 and is equal to f minus x beta upon sigma. Small f y of y given x is now equal to capital F star of 0 and is equal to also 1 minus f of x beta upon sigma. The density function f of y given x is equal to n into x beta comma sigma square raised to power d into 1 minus f of x beta upon sigma raised to power 1 minus d. So this density function fy given x is now equal to 1 upon root 2 pi sigma square into e raised to power y minus x beta square minus 2 sigma square whole raised to power d. So in a way it is the power d of the normal distribution into 1 minus f of x beta upon sigma raised to power 1 minus d. Now the log likelihood of the same could be written as L is equal to d into ln into bracket 1 upon root 2 pi sigma square into e raised to power y minus x beta square upon minus 2 sigma square plus 1 minus d into ln 1 minus f x beta upon sigma. Let me clarify. I am sure you can see that this first expression after ln is nothing but the density function of a simple normal distribution. Now appendix gives the details about the Tobit model censored from the above, and the log likelihood in that case is given by L is equal to d ln bracket 1 upon root 2 pi sigma square into e raised to power y minus x beta square upon minus 2 sigma square plus 1 minus d into ln f of x beta upon sigma. So students, you can compare these two log likelihood functions and you can see that the first expression is same in both the cases. In the second expression, you can see the difference is only in terms of the log function of the second term, whereas in the first log likelihood function we have the ln of 1 minus f, whereas in the second case we have the ln of the f function. Let us take an example to understand this. Consider the situation in which we have a measure of academic aptitude, and let's say we have scaled it on 200 to 800, which we want to model using reading and maths test scores. The problem here is that students who answer all questions on the academic aptitude test correctly receives a score of 800, even though it is likely that these students are not truly equal in aptitude. The same is true of students who answer all of the questions incorrectly. All such students would have a score of 200, although they may not all be of equal aptitude. The density plot of aptitude given in figure 5, looking at the above histogram, we can see the censoring in data, that is far more cases with the scores of 750 to 800 than one would expect looking at the rest of the distribution. Now this can be treated as a truncated or censored model from above at 800. So we have the plot and you can see that how we have in a way censored the data in the last histogram. Now we can model the above problem using either OLS or Tobit model. Now results obtained from estimation of both the models is given in our table 1, which we will just now consider. So for a 1 unit increase in the characteristic read, there is a 2.7 point increase in the predicted value of aptitude in case of OLS and 2.9 in case of the Tobit model. 1 unit increase in maths is associated with a 5.7 unit increase in the predicted value of aptitude in case of OLS and 6.3 in case of Tobit model. So you can see how we are trying to link the scores on reading and maths performance on the aptitude of students. We can see that the OLS underestimates the effect of both the parameters read and maths on aptitude. So you can look at this table which is of our regression output, and the first column gives you OLS results and the second table gives you the results of Tobit model. We have the dependent variable which is aptitude and the explanatory variables or the linking variable reading and maths, and we have the constant values. You look at the second table in which we have the marginal effects of OLS, Tobit model, censored model and truncated model. So if we look at the marginal effects given in this table too, we can see that in case of OLS, the marginal effects are same as the regression coefficients, but not in the case of censored and truncated model. The marginal effects are higher in the case of censored model in comparison to the truncated model. Now these marginal effects have been obtained at means. Censored regression treats all values above 800 as 800 and thus shows a higher marginal effect in comparison to the truncated, which leaves those values altogether, which is graph 6. We have the censored and truncated marginal effects. So we have different marginal effects on the y-axis and we have the maths and reading or read on the x-axis. So you can see that this graph 6 shows the marginal effects of maths and read on admission as the score on maths and read varies. The marginal effect of read is higher than the maths, and regression coefficients and the marginal effects at means also suggest that. So the marginal effect of both are constant in the beginning but declines after that. We can also see from the above graph that the censored marginal effects are always greater than or equal to the truncated marginal effects. So dear students, let us now try to summarize what we have learned so far in this module. Estimation of OLS is not dependent on the normality. It comes later while making statistical inference. But I am sure you must have observed that in case of Tobit model, the distributional assumptions are inherent in estimation also, as truncation and censoring has to be brought by some distributional assumptions only. This extra assumption in Tobit differentiates this from the normal OLS estimation. The OLS suffers from overestimation or underestimation of marginal effects, and that is where the Tobit can be useful. The idea of truncation and censoring should be used properly to get the correct marginal effects.